So thank you very much for having me, and thank you for the organizers, to the organizers as well. It's been a really wonderful conference, and it's really amazing to come and get to speak to you all and get to know you better. And yes, it's going very, I think, a very successful conference. So I'm going to be talking about a couple of things that kind of relate a little bit with Melissa's talk before. So Melissa was talking about combinatorial game theory. She mentioned that there's these three notions that make these combinatorial games so beautiful: the perfect information, having no chance, and having two players. So I'm going to talk about some games where we keep somewhere between 0 and 3 of these properties. So I'm quite interested in games that are played on graph that kind of resemble a pursuit evasion kind of a setup. And because we leave things quite, yeah, okay, no, okay. I won't continue with that thought. Okay, so I'm going to be talking about a number of different papers. So there are two sets of co-authors here. So, okay, so let's. This is a design. I'm aiming for a design theory kind of an audience here, but let's get into the definition of what the parameters are that I'm going to be talking about. So. The first game that I'm going to introduce is not the main one I'm going to be talking about, but it's such a central one to this area in pursuit evasion. So we play the cops and robbers game on a graph. So firstly, we play it on a graph. There we go. Okay, we play it on a graph G. We play with k cops. The cops will reside on vertices of your graph. You have one robber, which is also on a vertex of the graph. You have the cop player turn, and then you have a robber player turn, so you alternate. Each cop will move from a vertex to a neighboring vertex in the cop's turn, and then the robber will move to another neighboring vertex on its turn. So I accidentally missed out this last line. The cop will win if they ever share a vertex with the robber. So that's the kind of end goal here. So the question is, okay, how many cops do you need? So there are some graphs that if you play on, you'll see, well, if we just have one cop, it's not sufficient to catch the robber. And so we define this parameter C of G to be the cop number, which is the minimum number of cops that you need given that particular graph. So let's have a little bit of a look here. So let's suppose that we placed the first cop. So this is the initialization. Then the robber comes along and they initialize somewhere. It's the cop's turn, so they decide to move along to a neighboring vertex. Well, now it's the robber's turn, so they can just move away. So this is not a one cop win graph. You require 2 cops to win here. Here is another one. So this is, I believe, an instance graph of a projected plane. Picked because it's what we'll be talking about later on. So let's suppose that the robber was here at some time point. So this is just a bit more of a complex example. Let's suppose that we were playing with 2 cops and that the 2 cops were somewhere, right? So you're playing along, the robber doesn't move because it's not attacked, and then all of a sudden at some point, one cop moves into a neighboring vertex and so kind of attacking the robber. And maybe there's another cop as well. So let's just suppose that the other cop moves closer. Well, in this situation, the robber has kind of an escape path. So hopefully we can kind of see here that if you have some kind of a graph that has a relatively high minimum degree and you have girth, it's actually girth 5, then you need a lot of cops. Okay, so Meyniel's conjecture is a conjecture which has really spurned a lot of research in this area, and it's the question of what's the ratio of COPs you need to the number of vertices. So if you have n vertices in your graph, we're talking about the square root of n. The conjecture states that with the square root of n vertices, or asymptotically the square root of n vertices, that you will be able to catch a robber. Sorry. With the square root of the number of vertices, that amount of COPs, you're able to catch the robber. Sorry. So this is known as Meyniel's. This is Meyniel's conjecture. Such classes of graphs are known as Meyniel extremal, and we don't have very many of them. So I should also say there is this, however, even if you could show that it is asymptotically n to the power of 1 minus epsilon for any epsilon, that would be a big improvement. So we don't even know that. But this seems to be, based on the evidence, what it seems to be close to. So we don't have too many. There's been kind of three phases that have been introduced of Meyniel extremal graphs. So the first phase was these incidence graphs of affine and projected planes. And then Anthony and Andrea extended that and looked at other designs, the incidence graphs of other designs, and they found here's another whole bunch of Meyniel extremal graphs. And then somewhat recently, the some abelian-Cayley graphs have also been introduced that are Meyniel extremal. So there aren't many of these things, but the ones that we have, well, the ones up here, are based on designs. And so, so we're going to investigate this a little bit more. This paper came out in 2020, which looked at a variant of the COP number. In this variant, there's a lot of different variants, but this is a variant that was studied, which is quite interesting, where rather than just landing on the COP, you actually have to completely surround the COP. So the idea is that you encircle you have to encircle the robber. Sorry. So the COPs encircle the robber and yell out, "You're surrounded. Give up." So this parameter, it's a similar parameter, but it's going to be an upper bound on the COP number. And then the authors of this paper noted that that the surrounding COP number can be large. It can be larger than the square root of n, but when it is larger than the square root of n, all of a sudden the COP number collapses. Yeah. So if we want to know, if we want to perhaps prove that the square root of n is an upper bound for the number of COPs, maybe this is a good way of going about it. Looking at other parameters that are similar and seeing if we can perhaps prove it that way. So I came to a very similar conclusion when I was working on localization. I kind of thought maybe if we looked at localization, we could get some kind of an upper bound implied. And so then I came across this paper and realized they'd beaten me to that idea. But that's the kind of direction that I've been going in this research. So to speak on localization, this is another game where you have a robber, but now the robber is invisible. The COPs don't know where they are. You again have k-COPs, but the k-COPs can go anywhere on their turn. And if a COP chooses a vertex, they find out their distance to the robber. And then the question is, okay, you get all these distances together, you knew where the COPs were, can you locate where the robber is? So this is very close to the metric dimension property for graphs. So we're going to label this, again, the number of COPs that you need in order to be able to localize. So localize, we're allowed to have as many rounds as we like. The robber's only moving one vertex at a time, and the COPs are probing every single time. But the smallest number of COPs that you require here we're just going to label as zeta of G. Okay, so let's have a little bit of a look here. So here's a graph. We don't know where the robber is. We play with one cop and we come and place the cop on this vertex here. If the cop probed a distance of 0, we would know where the robber is, and so we would be finished. If the cop probed a distance of 1, well, there's only one vertex, which is distance 1, so we would know where the robber is. So therefore, the robber, knowing in advance what the cop would do, would want to play on one of these outer vertices. That's the only kind of sensible thing for it to do. Then the robber gets their turn. Sorry, this is not right at all. So the robber could be on this vertex, or this vertex, and they take their move, and they can move into the central vertex. But then in the next turn, if the cop plays here, well, then the robber can't be on this vertex without capture, can't be on this vertex without capture, so you've kind of reduced the robber territory. Then you can do that again. It's the robber's turn, then the cop's turn, and now you've finally deduced where the robber must be with 100% confidence. Yeah, so this is an example. That's an example of a one cop win localization game. Yeah, so we started going through, and we wanted to say, well, these Meyniel extremal graphs have been very, very useful for the cop number, and because they have some kind of a there's a whole bunch of properties that make it the cop number to be very large. So what about if we study other variants? So we did study this localization number on the incidence graphs of projected planes and affine planes, and found that if you have the projected plane of order q, you get localization number q plus 1. So this is asymptotically same as the square root of the number of vertices that you would have in that graph. And this also matches the cop number too. So we have this kind of phenomenon where the cop number here and the localization number are the same. And so a similar thing for the affine plane as well. So we went through and we studied a whole bunch of designs that had their cop number studied. So we also did some BIVDs. So here we also looked at some Steiner systems. So I guess one thing which I'd kind of like to convince you about with the connection between these games and designs is that I think that it can be a bit of a good two-way street. I think that if design theorists think about these problems when they're looking at their designs, we could get some really good designs that might prove what we want to prove in these pursuit evasion games. But I also think it can be a little bit of the other way as well. When you're studying these various different parameters, I think you can actually get some structures within designs which I think would be actually quite interesting. So this one isn't too much of something of a structural interest, or it's very well studied already. So if we look at a Steiner triple system, the idea within this one is you want to get a whole collection of non-intersecting blocks, and you want to get as many as you can. And if you get that, then you can use that as a basis of your localization. And so this term here, so we're saying the localization number is at most this one here. So this value here corresponds to how large of a set that you'll be able to get. Yeah, so this is also, once again, we get this design which is quite nice, and we find that the localization number is approximately the square root of the number of vertices too. Cool. So we're able to do something very similar with Steiner Systems. Again, so we have now that the blocks are of size k, and we can go through and try to partition our v points up into blocks of size k, as well as we can, and we have some extra points that we can't cover. but within the localization game, we're able to find various different techniques to overcome that. And so we're also able to do that for when t is not just 2 as well. Okay, so we have a whole bunch of designs, and we now have a whole bunch of bounds. And a lot of the time when we have these, we have a whole bunch of upper bounds. Some of these we have lower bounds for, some of these we don't. However, when you kind of study these things, you almost get certain that these upper bounds are tight, but the lower bound is just hard to prove. So there's a very dynamic nature here. It makes it very hard, but within designs, the robber can, if you don't catch the robber can escape very quickly. So you really have to kind of encircle it. Yeah, cool. So I did also say that I was going to look at a couple of other things as well. So we also, we observed that, okay, we've just talked about bipartite graphs, which are quite regular, and we want to try to see how much we can kind of push this. The diameter was quite small, so we came along and said, well, what if we have graphs that have got a lot of structure and have a small diameter, and so in particular diameter 2. So we came along and we looked at the Kneser graph was one of them. So this is a Kneser graph 2,6. Every vertex, or for every unordered pair within your set, you have a vertex, and you connect 2 vertices if they share no elements. So for example, 1, 6 is connected to 2, 5 because 1 and 1, 6, 2 and 5 don't share anything, but 1, 6 is not connected to 1 and 5. So this is an interesting graph, and a graph with a small diameter. You don't have all of the edges, but you have a lot of edges in there. So we can ask for how we could localize this. And we came along and looked at these various resolving sets. So in gray, I have a resolving set, which means that the cops would be able to win on 1 turn if they played on those vertices in particular. So if the robber was on 1, 5, for example, then this vertex here would tell you that it's a distance 2 away, and 3, 4 would tell you that it's a distance 1 away. So by knowing that it's distance 1 from 3, 4, you know that 3, 4 is not in it. By knowing that it's distance 2 from 1, 6, you know that either 1 or 6 is in it. And so you can slowly deduce what that would be. But it turns out that this actually relates to what I think is quite a fascinating problem. So if you get a resolving set here, you can get each of those vertices and then look at them as if they were actually hyper edges within a hypergraph. So in this case, it would be just a regular graph, not a hypergraph, but you would have an edge between, you'd have vertices 1 up to 6, and you'd have an edge between 1 and 2, an edge between 5 and 6, an edge between 4 and 5, an edge between 3 and 4, an edge between 2 and 3, and an edge between 1 and 6. So you would get a graph, and in this case, it's a cycle. And then on a hypergraph in general, and it would be k regular, and we can say this next thing. So, oh, sorry, not k regular. Sorry, I said k regular. I meant k uniform. You end up with a k uniform hypergraph on n vertices, and we can come along and define a game which is on hypergraphs, which is being k detectable. So the general idea here is that you've got some k uniform graph, you've got a lot of hyper edges going everywhere. If you were to burn one of the vertices and then get a list of all the edges that contain that vertex, could you find out what vertex was burnt? And then, okay, well, that's not too hard of a problem. But then if you came along and you burnt 2 different vertices, and then you got a list, just one list of all the edges that contained a burned vertex, then could you go back and discover what those 2 are? and then you kind of keep going. Well, would you be able to do it if there were k different fires? So this is, you're able to find out where every individual fire is just from the hyperedges that were burnt. Just one list of hyperedges that were burnt. So playing this game on these hypergraphs that came from the Kneser graphs, we found out that actually playing these two things are the same thing, where the number of hyperedges you have to have on this hypergraph is going to be the cardinality of your resolving set. So that's going to get you your localization number there. So because of that, you can go through and study this hypergraph property, and you can go through and say, how big does your hypergraph have to be in order to get this property? You can go through and say, well, the sum of the distances, the sum of the degrees of any two vertices have to be a certain size, and then you can go through and deduce the minimum size of such a thing. And then we're actually able to find a hypergraph that exactly matched that, or asymptotically matched that. And so we were able to show, this is for the even case, we're able to show asymptotically tight equality here of n on 2 plus n on k. So that was quite nice. And so the Kneser graph had been studied before, so this was a big improvement there too. So we also studied the Moore graph. So we found that if you have a Moore graph, which is k regular, you get one of k minus 1 or k. So that's kind of what we were saying before about having this approximately square root of n number of vertices asymptotically. We also looked at some polarity graphs as well. And so we're able to get similar kind of results here. Again, more localization the localization number is again asymptotically the square root of n. Yeah, so that was the second project. So one that I'm going to just brief over. This is a recent one a recent project that we did. We're looking at the Latin square graph. So the idea here is that you have a Latin square, you can turn it into a graph. So a graph on n times n vertices, where any two vertices share an edge if they're in the same row, the same column, or they share the same symbol. So we've got our design, we've turned it into a graph. And so we're able to show a number of things with this. So the COP number, we generalized this. We had Latin squares, then we went to mutually orthogonal Latin squares, k mutually orthogonal Latin squares, and you can define a graph in a similar kind of way. We're able to show that the COP number is, so it's not an example of a Meyniel extremal graph, but it's still very large compared to other examples that we have. Then we're able to do the localization number. I might just skip over this result. I was going to explain a little bit more. But this is one thing one result that I quite like. We're able to get an upper bound on the localization number that was upper bounded by a minimal cover of a Latin square plus some term. So one really big thing that we just studied within Latin squares is what I call Bernoulli's conjecture. So what is the largest size of a partial transversal within a Latin square? And this is a problem which has also had a lot of interest. And so we're able to get that, if we're able to find a maximum partial transversal of some Latin square, which we have bounds for within the Latin square theory, that gives us also the bounds for this property here. And again, there's this kind of idea that it feels that this is the best that you can do. It seems almost impossible to be able to beat this. So I suspect that this is also going to be a lower bound here. So again, this kind of idea that we're studying these games on graphs that are based on designs, and it seems to keep connecting back to important things which are studied within designs, and it keeps bringing up these kind of interesting structures within designs. So I think it would be really interesting to come along and connect some more complicated designs and more complicated ideas within design theory with some more complicated ideas within pursuit evasion, and see the kind of cross benefit that would come from that. So there's a lot of people here which I think are very impressive. Someone was talking about their Stinson number yesterday. I realized I have Stinson number 3. So compared to other people in this room, that's very much not impressive. So I thought I'd map it out a little bit, and I am I believe that's 7 edge connected to Doug. Then I would kind of wanted to leave on this little point here about the future of the Meyniel conjecture. I was kind of wondering, well, actually there's going to be a lot more edges in here connecting all of these people. It's not going to be a complete graph, and so there's going to be a lot of edges, but not too many of them. The degree is probably going to be quite high. So actually, this seems to be like the kind of graph that we might be after. So a couple of things that I wanted to kind of leave you with with this problem is we're looking for graphs that have their degree or the minimum degree or the average degree to be actually we found to be the less than the square root of n. We actually need it to be smaller than the square root of n if we want the copy number to be high. That's a new result. We probably don't want the diameter to be very large, but we need a complicated structure in order to be able to do it, but we also need to be able to analyze it. So yeah, I thought I'd kind of pointed that this seems like maybe this is the kind of graph that we're after. So I'm going to thank you very much for your attention.